So, hello everybody. We have Vaibhav Kalvakota with us, who's gonna present on essence of LLMs and transformers. A word about Vaibhav. He has been doing high energy physics, but recently he has switched to machine learning. And yeah, so let's hope to learn from him today. Okay, over to you, Vaibhav.
Okay, so thank you, and I hope everyone's having a good day. Um, so basically, these slides were taken from my notes. So the one is basically from there. So the notes were called Essence of LLMs and Transformers. I just copy pasted the title, but and originally I was about to talk on some of the novel stuff happening in adaptive sparsity transformers, but I decided to keep it a little pedagogical because I think it would be a good experience to just get a feel for what LLMs are, and seeing as there's a huge boom for LLMs and transformers and a lot of other aspects of neural networks. I think it's nice to just get a good motivation towards what these things are. And so this is based on a number of things. Excuse me. This is based on a number of things. So the first thing this was based on is a mini paper that I'll be putting out in a while. It was supposed to come out last week, but I decided to do a bit more coding. So this is based on adaptive sparsity transformers, which is a paper I'm hoping to complete this week. There's a short note which will be posted on my website at this URL. It should be online, I guess, by tomorrow. And it's loosely based on a mini course of lecture notes that are of this title right here. And yeah, none of these are actually online yet. I think the notes will be posted tomorrow. The paper should be out this week or next weekend. Okay, so I'll just start by saying that natural language processing is very important because as humans we can just quickly think about answers. If someone asks us a question, we impulsively can answer it without having to think much about it. And in CS, NLP is a very important field because you're trying to make the computer human in a sense. And of course, there's a lot of subtleties with that. But one of the subsets of NLP is large language models. And the goal of a large language model is somewhat straightforward. It is to, in some sense, if you took the case of text to text, for instance, it is to basically be able to interact with a human at the level of a human. So if you would ask it a question such as this, so why are polar bears cute? There's a number of relevant tokens here, a number of relevant inputs here. So the first relevant input is polar bear, which is an animal, and then there's the word cute, which is a characteristic, and then there's a why, which is the input question, so the output has to be an answer. And so the output that ChatGPT will give you, I think with Forum Mini, is polar bears are often seen as cute because of a combination of and so on and so forth. And basically, it creates a sentence based on the input prompt. So what GPT is well, I think from its title itself, you should be able to guess it, which is it's an adaptive, it's a generative pre-trained transformer, which is to say that it's an autoregressive generative model, and it's a pre-trained transformer model, and the transformer in itself is the neural network architecture. So there's very large chunks of data and parameters to be trained, and it's a three-stage process where you basically start by taking that you get from pre-training, and then you fine-tune it. So you kind of update the parameters based off of supervised fine-tuning or reinforcement learning with human feedback, and you keep repeating this until you get at least optimally, you get a decent enough production-grade model. And basically, to work with the large language model itself, we want to work out these in very large chunks of data. So often these are terabytes of data. And once you obtain a base model, you can fine-tune them and make the model better. And you would expect that bigger chunks of data would necessarily mean the model is better. But in some cases, you can distill your model and make it smaller so that it kind of fits the use case better in a process called knowledge distillation. But essentially, what you want to do is you want to optimize these parameters. So LLMs fundamentally are as follows. So, and this is the text-to-text scenario.
I have a question. What does this optimization do? What does this optimization mean?
So this optimization means if I have some, scenario such as a prompt, which is basically asking a question, it could be a very simple question.
Mm.
So I could ask it, there's in fact an example right in a couple of slides, which is, if I have 20 apples and I, give away 6 apples and then I give away 2 apples and I give away 1 apple, how many apples do I have left? And the thing is, your base model will never, be the optimal model. So there's always going to be something that's going to miss. Maybe it gives you the wrong output. Maybe it can't generate the sentence properly. Maybe it's just giving you a trash output or none at all. So basically, when you're trying to optimize your model, what you're trying to do is you're trying to optimize these parameters or these weights, and you're trying to make it so that the output is as accurate and as concise as possible without taking too much processing time. So you want to have a nice trade-off between the computational complexity of the model itself versus how accurate it is. And basically, you're trying to optimize that ratio. So it shouldn't take too long, and at the same time, it shouldn't be inaccurate. So faster but inaccurate is not as good as the model output that you would naturally want.
Okay.
Yeah, cool. So let's suppose that you had a sequence of n words. So this is just a sentence or maybe a question, or maybe it's just a statement saying I want to learn more about the history of Poland or something like that. And suppose you had a sequence of n words and you wanted to train a model to predict the next word. So you want to find the probability that the next word given n minus 1 words is xn. So over here, I don't think my pencil has, yeah, it doesn't. Excuse me. Basically, what you're trying to do is, given xn minus 1, the bold face meaning that there's x1, x2, x3, and so on and so forth until xn minus 1 input words, you want to predict what the probability is so that the next word is the actual output word, which is xn. So given these context words, which are xn minus 1, what is the probability p of xn that the next word is xn given these context inputs? So there's 3 things here. So the first one is you want to keep a track of all of these n minus 1 inputs. So you want to make sure that given these context words, over long sequences of words, over long sequences of inputs, or maybe paragraphs, you want to be able to keep a track of all of these inputs. So if it's a question, it needs to contain the question contextualization. If it's maybe asking about some particular characteristic, you want to be able to map that, and so on and so forth. And the second thing is you want to be able to encode positional information. So for instance, how did the cat eat the cheese is different from how did the cheese eat the cat, which is obviously a garbage, which is a garbage question because, as a human, we can easily identify that we're talking about the cat eating the cheese. But if you can, kind of contextually make these different, so if you replace cat with cheese, which is just, 2 input tokens being misplaced, you get a completely different meaning. And in some cases, it doesn't have to be that difficult either. You could just say the chicken couldn't cross the road because it was too wide, which is an example that I saw in Jarofsky's Stanford Notes. And so in that case, the it refers to the chicken, the it refers to the road, not the chicken. So there's, depending upon the context, there's a lot of positional information. And the third thing is that you want to optimize this model in all sorts of ways, which we'll get to in a moment. And so the how is we want to be able to encode positional information with weights, positional weights. We want to add contextualization over long sequences. And all of this basically boils down to using different sorts of neural networks. And then we basically obtain a base model, which gets you to the first stage in this 3-stage process. So that's the pre-training. So basically you give it large chunks of data.
Yes,
you give
so is it question to just conditional probability or is there some more meaning to it?
I'm sorry, I didn't get you.
Question 2 is just looking at a conditional probability. Given this event, you want to find the expected. And the probability of action given you know the action minus 1.
Yeah, so basically what you're... Yeah, go on, sorry.
No, yeah, I just wanted to say, is it just conditional probability or there's more to it? Just seeing that.
Oh yeah, this is just conditional probability. So yeah, I mean, I was just trying not to include like intimidating words, but yeah, this is actually just conditional probability. So given these n-1 context words, context inputs, you basically want to find the, the probability, the conditional probability that xn would be the next output. And in fact, every,
Hmm.
such, anything that kind of rings statistics or probability theory to you is actually statistics or probability theory for that matter. So yeah, actually,
Ah,
right. So yeah, so this gets you to the first part, which is pre-training, where you basically filter out a huge, more or less generally public domain training data. You kind of filter out things that might ring unethical to you, which I'll get to at the end. And then you kind of train your model, you obtain a base model, and from there you try to make it better. And this is not as easy as it sounds, because I probably made it sound a little too easy by saying that these are the three things that we're talking about, but there's a lot more to it, as you'll see. So yeah, so the purpose of these autoregressive generative models, which is a fancy term for just saying you're making a large language model, or a model that basically predicts an output based on an input prompt. The thing about these is trying to make um, you're trying to make the model generate a meaningful output, but the way you do this needs a lot of tweaking. So the problem statement or the objective statement of here is you want to make an NLP model that can understand meaningful contextualization of inputs in a sequence. So x1, x2, so on and so forth until xn. And usually these context sequences are kind of limited, because otherwise you just have, completely, garbage inputs, and the model wouldn't really be able to understand the context of that, because there's a lot of complexity with it. And you basically want it to generate a meaningful output. Now, how do you do this? So the first example was that of the vanilla recurrent neural network model, which would store a state. And so, yeah, this is where my physics side comes out. So the state is never denoted by psi, but what can I say? I love living with states. So you basically store a hidden state based on the first input. So let's suppose you're starting at input, let's say t equals I, and it kind of updates a hidden state psi at t equals I, and then it would process the output for that input, and then it would take the hidden state as the as a sort of an activation for the next hidden state. And so that hidden state gets mapped with its corresponding input, and then it generates the output and so on and so forth. So just to give you a better idea of this, so let's suppose that xiti is let's suppose that this is the input at some time t equals I, and then we store this in a hidden layer, a state psi t equals I, which will be passed on to the next input. And so this is a schematic for this. So basically you have xt, which is your first input, which updates some state in the hidden layer. So that's hl psi t. And that for that input xt, you get some output ot. Now you use psi t for the next input, which is xt plus 1 or xi plus 1. And you update the next hidden layer state, which is psi t plus 1. And then you generate the output for xt plus 1, which gives you ot plus 1. And then you take psi t plus 1 and update the next hidden layer state, psi t plus 2. And you take the input for that, and then you update it, so on and so forth. So basically, this is a forward propagating recurrent neural network with only one forward pass hidden layer. So basically, these you have only one hidden layer, which is forward pass, which is to say that you're going causally to the future. So psi t plus 1, psi t plus 2, and so on and so forth. You never go back.
what is
Um,
actually?
uh-huh.
What are these actual? Actual minus IT? What are these actual?
Oh, the issue is just it's actually just a word actually. Over here is just saying that this is a hidden layer. It's not a minus. It's just saying that all of these states are just hidden. So they're all going in the background. So all of these psi t's are just being updated for every single input, and all of these psi's are basically in a hidden layer. So that's what the HL represents.
Hmm.
Right. So now this is not really sufficient, because in some cases you could have context in the future. So there's an example coming forward, but I'll just get to it. So there's basically bidirectional recurrent neural networks where there's a forward and a backward propagating hidden layer. So in this case, you go psi t and then psi t plus 1 and then psi t plus 2, and you basically update the inputs in that fashion. So you're updating the inputs in a causally future pointing direction. But in the case of bidirectional neural networks, you get a lot more context. contextual information, because in some cases the context could lie in the future in an input sequence. So when you say I love Dune Part 2 or something like that, and you were supposed to predict what the word was, so if it's I dash Dune Part 2, the context lies in the future. So the thing we're talking about lies in the future. So it has to update the context backwards. So in this case, that's what's going on, right? So what it's basically doing is, given some input psi t minus 1, I'll actually start with psi t. So given some input, xt, you update a backward propagating hidden layer and then a forward propagating hidden layer. So basically, you're updating two states, not just one. So for xt, you update a psi t, which goes to the future, and then you update another psi t, which goes to the past. So in this way, there's two contexts over here, as you can see. So the first context is this one, which is going backwards. So the states go psi t plus 1 to psi t minus 1, and then it kind of updates it that way. And then there's a second context over here, which goes in a possibly future manner. So it goes psi t and then psi t plus 1 and then psi t plus 2. And that kind of updates the inputs, and that allows you to basically recover contextual information from the future and not just the past. Because in the case of the vanilla or the original neural network, recurrent neural network model, you could only go forward. So the sequence was always supposed to propagate forwards. And the thing about recurrent neural networks is there's two issues to begin with. The first one, and both are actually related. The first one is this sequence is, it basically has to do with, this causal sequencing. And because it can only take the inputs from its previous or the next layers, if you have a really, really long sequence, the context, let's suppose the context is something like 100 words or something, then this long-range dependency of the context will actually be lost. So X2 input will not really be able to correlate with, let's say, X99 input. And so you're actually losing a lot of context over here. So that long-range dependence is actually being lost. And related to this is the issue of something called vanishing gradient, which is that you're basically just losing a lot of contextualization. The thing about LSTMs or long short-term models is that long short-term memory is that these models are very good in comparison to recurrent neural networks in the sense that they don't have this vanishing gradient problem, and you can actually keep a track of what information you want to keep a track of and what you don't. But I won't really talk about LSTMs because I think it's really complicated to kind of summarize into a quick talk. But the thing is, both of these, while very, they work for their use cases pretty well. The thing is, they have to do this causally. They have to do this sequentially. So there's no way you can parallelize this process and compute the context or the relevance of each input with other inputs in the sequence at once. So this, these models are very, very restricted in that sense. And so the breakthrough came with this paper, which is Attention is All You Need by Vaswani et al. From Google in 2017, which is very recent. And yeah, I think this is okay. So this is the first page of that paper, and this is one of the. In fact, this is one of the coolest papers that you can read, and this is the coolest paper in CS as far as I know. And this paper basically presents the transformer neural network architecture. And what this does is, what they did was they kind of said, okay, we'll just start from scratch. So instead of building everything on top of updating state, instead of doing something like, okay, we have an input and then we'll update some state, which goes into a hidden layer, and then updating the next state, and so on and so forth. We'll actually take the context, or we'll take the input, and then we'll assign some self-attention to the whole model in the transformer block. And so basically, what you're doing is for some input xt at some time t, if you're not really computing the correlation with just xt plus 1 or xt minus 1, you're actually computing it with every other input in the sequence, which means that the complexity is high, but you can actually parallelize this. So if you're running a transformer neural network on a GPU or a TPU, you'll actually not face much of an issue, assuming that your use case actually necessitates it kind of requires it, because in comparison to recurrent neural networks and RNNs, LSTMs, you actually have a much higher memory usage and complexity, as we'll see. So yeah, this is the extension is all you need paper. But the thing is, okay, like I said, I kind of probably make it seem a little too simple. But the thing is, these machine learning models are very, very computationally expensive. And base large language models, the actual coding part isn't probably that hard. The thing is, you want to optimize it so that it doesn't, take a huge training data set and give you a really trash output. And the thing is, it's also very expensive, both computationally as well as financially, because the thing is, you need a lot of GPUs, which again, computationally and financially kind of necessary. And the second thing is, if you have a bad model architecture optimization, it also means that your model in itself is bad. So it's not just about, oh, well, it takes, way too long for this code to run and to, process this training data. It's more so the fact that even if you can fine tune it as well as you can, your model will still be bad. And that kind of completely ruins the model in itself. And so the thing about transformers is that instead of having to, encode context into every single word on the basis of, where in the sequence it is, it kind of positionally encodes it, in a different fashion. I wouldn't be getting into the details of any of these actually, because I don't think, it's, well, firstly, it's way too mathematical, and secondly, I don't think it's something that can be covered in an hour. But so the thing about transformers is that they kind of, encode positional information by tokenizing. So it's not necessarily words, but instead it could just be a sequence of letters or characters or whatever. So if you had the word beautiful, you could just take everything until beaut, B-E-A-U-T, and then you could take ifl as a separate token, because in some cases, you would just want to say that that's a separate token that's being attached to some other token. So for instance, the ifl from beautiful is also being applied in merciful. So the thing is, you kind of tokenize the whole vocabulary, and then you kind of take your input sequence, and what you do is you take the entire lexicon, and then you kind of just, you kind of tokenize that. So given an input sequence, sigma, you basically just tokenize the whole thing, and then you give positional encoding. So let's suppose you had an input that said, okay, I don't want to invoke Dune again, but let's suppose you had machine learning is cool. So what you do is you kind of give some positional weights to every single input token, and then you kind of process the sequence instead of having to necessarily update every single token at every single step in time. But perhaps the genius of the transformer model is that it uses something called self-attention, and that is what makes the transformer model. And because fundamentally, the only thing that kind of concretely separates a transformer model from RNNs or LSTMs is that it's just self-attention plus a multi-layer perceptron or a multi-layer neural network. And so optimization involves making the model faster. So it could be kind of taking different parameters and assigning slightly retrained parameters after you do something like supervised fine-tuning or reinforcement learning with human feedback. And it has to be productive so that it doesn't generate garbage or completely out of context outputs. And you make it more efficient so that in general, if you have a really huge language model, you have to make sure that the use case for which this model is being considered is actually being used, because it's not really advisable to train a really huge large language model only for it to end up being used by users to find out the number of peas in apple or something like that. So in that case, you would do something like knowledge distillation, like I said. But yeah, so we're in a really good place. So fundamentally, we have transformers, which are better than RNNs and LSTMs, and they're much more computationally expensive with GPUs and TPUs, and they're not really that bulky to work with. And I think the most concrete examples for this would be the GPT, Cloud, Llama, or Gemini models, which are really they're really very productive. They're very efficient, and I think they're the most popular and the most effective large language models in the world right now for text to text. And of course, there's different use cases because transformers don't necessarily mean you're restricting yourself to a text to text NLP model. It could be anything. So technically, you could just work that out into an image classification or something like that as well. But fundamentally, what you're trying to do is just optimize your model so that whatever the output is, it does it better instead of just giving you some arbitrary overfit data or something. Okay, so now let's actually just summarize everything. So in terms of the jargon for large language models, so once you obtain the base model, what you try to do is fine tune it. And in order to do fine tuning, you kind of just retrain all of your parameters. Or in some cases, you'd select which parameters you're actually retraining, because otherwise it's a computationally very expensive process. So what you would do is you would obtain the base model so after pre-training, and then you would soft launch it for testing. And then the next step would be fine-tuning, where you, like I said, you update the parameters. And in some cases, you would use parameter-efficient fine-tuning, so that you select which parameters you're having to go through again. You would update the weights, and then you would use gradient descent algorithm to minimize the negative log likelihood again. So this is, again, just standard machine learning optimization. You're trying to minimize the loss function, which here is going to be the cross-entropy loss function. And then you would fine-tune your select parameters to find the optimal parameters for the model. And then you could use reinforcement learning with human feedback. So what you would do is you would take this model, you would give it to a bunch of human testers, or in some cases you could just automate it, and you would try to maximize the reward with human feedback. So a human would actually test it. They would say, oh, well, this is what's wrong with the output prompt, or maybe this is what's going wrong with its predictions or whatever. And you would just kind of fine tune it that way. And then you would obtain a better model. And then you go back to the first step, and you have a new and better optimized base model, and then you would just keep doing this. And so the thing is, a huge misconception is that when the transformer model first came out, or when self-attention first came out, it was necessarily the version that we see, because it would have been easy for a transformer model to be just a causal language model. So it would have just been, okay, I'm calculating the attention for some token at some time t, as I don't want to get into the details again.
Sorry, I have a question in your previous page. Can you go back to
okay.
What is this minimize negative log likelihood?
So what you basically do is when you have a loss function, so yeah, okay, this kind of appeals to the fact that you could just take the negative log likelihood, or you can actually just maximize the likelihood, that's fine as well. But the thing is, what you do is you take the negative log likelihood, you minimize that, and that's equivalent to maximizing how well your model is performing, which is calculated by the minimum of the loss function. So I think the best example, just to illustrate, would be the mean square error function. And what you would do is you would calculate the log likelihood, and then you would minimize that. And that is, that's basically equivalent to saying that you're minimizing the loss function. So in this case, yeah, you're using a particular form of the loss function, and then you kind of minimize how much error there is in your model, and then you continue with the process of fine-tuning your parameters and so on and so forth. So basically what you would do in a causally propagating large language model is you would take the attention weights, but you would only go forwards. So if you have some small t time, and you're basically taking that input, you can only go forward. You can only go backwards for getting the context. You won't be able to get context from the future inputs. So basically, you don't have backward contextualization, because your input attention correlations are only forward propagating. So in this case, when I absolutely blanked Dune part 2. Now, because the context is just forward propagating, it can only go up to the point where you have the input. It will not be able to predict love in the blank. And so the solution is that you do bidirectional language models, which is the exact reason why we did bidirectional recurrent neural networks. And in that case, the input correlations propagate throughout the entire input sequence. And so because of that, it would be able to kind of predict what the word in the blank is supposed to be after getting future context. So now it's going backwards as well. And the thing is, it's not always going to be so clear, and in some cases you'd actually have comparatively subtle improvements to be made. And one of those improvements is something called chain of thought. So improving the performance of large language models and evaluation benchmarks is very important. And well, two of the best performing large language models up to date is GPT-4o and Cloud 3.5 Standard, which are I think the front runners. Although on the on the language model arena leaderboard, I think there's a number of other ones as well. But okay, so 3.5 Sonnet performs better than GPT-4o in GPQ and human eval, and GPT-4o performs better in MMLU and mathematical evaluations. I think experience would just tell you that Cloud 3.5 Sonnet is really good for coding, whereas I think GPT-4o is better for more for something like an arithmetic task where you're basically trying to let's say do some particular calculation or arithmetic reasoning. It's much better than 3.5 Sonnet. And in these benchmarks, one of the many forerunner evaluation criteria, well, not so much criteria as much as characteristics, has to do with COT or chain of thought, large language models. So if I say, as an example, how many apples does Paul Atreides have? If he starts with 12, eats 6, gives 2 to Chani, and gives 1 to Silva, and basically you would just give this input prompt to your language model. A badly performing model could just say the answer is 5, for whatever reason. Maybe it doesn't do the calculation well, or maybe it's just a very bad base model or something like that. Now, when you give it COT, when you add in chain of thought processing, it could perform better on reasoning and arithmetic calculation benchmarks. And so in this paper by Wei et al. In 2022, they basically show that chain of thought improves their large language model, even though its original output was actually not so great. So over here, this is a figure from their, I think this is figure 1 from the paper. You see here that GPT-3 175B, which is fine-tuned, has a good solve rate, but then you have the prior best, which is 55%. And then you take the Palm 540B model, which with standard prompting only performs, it performs very minimally at 18%. But then if you give the same model chain of thought prompting, it actually performs much, much better. It has now 57% of solve rate on GSM 8K benchmark. And so the idea over here is that, these little improvements that you can make with chain of thought, and, when you're doing fine-tuning using something like low rank adaptation or LoRa or anything of that sort, basically all of these, little subtle but very technical details really matter. So how you optimize your model is heavily based on, how you can optimize your model with these improvements, these are definitely not minor, because you can clearly see that there's a huge difference between standard prompting and COT prompting for this model. But these are minor in the sense that unless you actually go, about thinking about how you can make your model better with, different techniques, you actually wouldn't be able to beat the, the more production grade models or something like that. And yeah, so I think on the leaderboard for language models arena, you actually have O1 mini, and this is for the coding. So this is on the coding benchmarks. I think I'll just, on the coding evaluation, with the arena scores being just ELO, you can see over here that O1 mini performs very well, and then you have O1 preview, and then you have ChatGPT 4o latest, and then you have 3.5 standard. And I think it's usually between these these 4. Although I think early versions of GPT-4o and Llama 3.1 have been really good contenders as well. So yeah, I think there's a lot of subtleties that kind of go into making a model better, and there's a lot of these mathematical artifacts that you have to take into consideration. And on that topic, again, when you're trying to optimize your model, there's a very, very huge, there's a practical limit to what you can do. So maybe your resources are limited, or maybe your time is limited. So how do you know what resources compute and how much time would it take to implement a large language model or train it or optimize it or whatever? And this is not a trivial question because you'll have to understand the scaling laws very, very particularly in order to actually be able to get a reasonable estimate for, how much time or how much compute it would take to implement a language model given, let's say it's of n parameters or something like that, n billion parameters or something like that. So yeah, so there's three primary factors to consider with these scaling laws. The first one is the amount of training data. And so again, like I said, while so in general, when you're doing machine learning, you know that more training data is better because it kind of helps you to mitigate issues like overfitting or whatever, or maybe it's just not performing particularly well and it just needs more training data or something. The thing is, when you have more training data, it's also increasing in a sense the complexity of of the language model. And so that's the first factor. The second one is what the compute and the resources are. So you could maybe have limitations. Maybe you have GPU issues or GPU limitations, or maybe you're just running it on Google Colab and there's like a 12 or a 24-hour cutoff, and that's not really well. Because I think the original transformer model for the English to German, if I'm not wrong, machine translation model, it took I think 3 or 4 days with 80 GPUs, which okay, we've had better GPUs come up after that, but again, there's a lot of limits to what resources, let's say, an independent startup could afford. And then the number of parameters and the complexity for fine-tuning are also things that affect your overall model architecture. The overall model complexity. And so there's other factors which are very, very, they're not particularly easy to just kind of keep an estimate of. Like, for instance, you could maybe have the neural network model itself having some, opposing some limitations, or maybe the vocabulary size or the number of, layers or anything. So basically, yeah. So this paper by Kaplan, Jared Kaplan et al. From 2020, gives a very, very it gives a very, very detailed estimation and analysis of these scaling laws. And what they do is they train a decoder-only transformer on websites too with byte pair encoding, and the vocabulary size is 50,000. It's over 50,000, and the context length is 1024, and the loss function is negative log likelihood minimization for cross-entropy loss. Right. So yeah, that's just a technical detail. I don't really think it's particularly something we have to remember for now, but yeah, basically, it's really worth it to understand that these scaling laws actually are very important.
What is meant by context size? Sorry, what is meant by context size?
So let's suppose you had. So let's suppose you had, so let's suppose you're using ChatGPT or something. You're using Flex on it. There's a practical limit to how much context it should be able to remember, because this context size actually increases the complexity by a very, very large order. And so because of that, if you have a really huge input sequence, it has to keep a track of more and more context, and it's going to be of a huge order. And so basically, there has to be a practical cutoff on what the context size is or what the largest input sequence is. And so that's basically what it's saying. And the vocabulary size is basically
the context size to be a big number.
Yeah, typically you don't want your context size. It really depends on, yeah, again, you have to make use of these scaling laws to be able to get a good idea for what your context size should be. In some cases, it could be something like 2048 or something, but for non-production grade or basically, if you're not OpenAI, AI, or Anthropic, I don't think you have a large context size yet.
I want my LLM to know what I asked it a week ago or 2 months ago, so that it knows what I haven't kept track of. No, see, if you increase the context size, for example, ideally, I want to know what I want my LLM to remember what I had asked it a week ago or 2 weeks ago or 2 months ago. So basically, ideally, I would want to, yes?
Yeah, well, I mean, the thing is, memory, okay, it's slightly different, because the thing is, if you want to keep track of everything, you could just kind of add in a memory updating feature. But the thing is, by the maximum input size, it is basically referring to, at this point in time, how big can I prompt it? So if I have some, huge input sequence, it can at most be 1024. It can't just be some really arbitrarily, huge, like, I don't know, Shakespeare data set or something, and then ask it like some really stupid prompts. So the thing is, there's a practical limit to how much you can run the transformer model given some input sequence. So that's what the context size is. Yeah, I guess, memory updating it's slightly different, but I guess it would be kind of closely related.
Okay.
Right. And so, okay, so here's the why to, why transformers. So why are transformers better than RNNs and LSTMs? And there's three factors, all of them actually kind of very closely related. If you follow this talk carefully, you'll probably realize this, because the first factor is that RNNs and LSTMs don't have parallelization, because you need the previous and the next context or the next state in order to infer anything about how I should update the hidden layer state right now. So if I have some XT input and I have some hidden layer state psi t, if I want to update this to get a better output, I need the context both from the future as well as the past sequences, past inputs in the sequence. So because of that, there's no parallelization. It's completely causal. It's completely sequential. So if there's x1, x2, x3, so on and so forth until xn, I can't take x2 and then calculate the relevance or the correlation with every other input, because it really doesn't make any difference if you do a parallel computation of this. And so again, just to restate that in a more elaborate fashion, at least for RNNs actually. So RNNs are strongly causal, which is it's a slight abuse of terminology, but the thing is, it's strongly causal in the sense that they depend on the last t minus n inputs, where n is greater than where actually this is wrong. You can't have so t has to be greater than n, but the thing is, it's at some point there's actually there's a practical cutoff to how many inputs it can actually keep track of. So yeah, I don't think I made a mistake over here. Okay, sorry. So the thing is, they can only depend on the last t minus n inputs. So the longer input sequence you have, the more likely it is that your inputs from very, very long ago are actually the context for those inputs is being lost. So if you have x1, x2, x3, and then so on and so forth until x, let's say 99, like I said, it wouldn't really have that proper contextual correlation between x1 and x99, because it's just a huge sequence. It has to keep a track of every single hidden layer state, so to speak. So it also has the vanishing gradient problem with respect to back propagation, which, okay, that's basically kind of related to it, but in fact, it's kind of almost identical. But the particular term with back propagation through time is actually it has a very particular meaning that I won't really talk about right now. But the thing is, if you have a bad long-range dependency, you have a bad model output, and the model correlation between inputs in the sequence for the model that correlation is actually being lost. Long short-term memory models actually correct this. They don't have the vanishing gradient problem. And the thing is, LSTMs are still kind of, they're still kind of chunky because they still don't have parallelization. But the thing is, transformers don't have this issue at all. And finally, the thing that makes transformers better than both RNNs and LSTMs is that they use positional encoding instead of, like I said, this, weird, chunky encoding of which word contributes to where in the context. And this is a very, very quick summary of why transformers are better, because, so when people say that transformers are better, they don't mean computationally their complexity is low. So I'll get there. So the vanishing gradient problem is significant in RNNs. It's not an issue in LSTMs, and it's not an issue in transformers. And long-term dependencies in RNNs are bad. In LSTMs, they're somewhat better. And in transformers, they're very effective. And the computational complexity in RNNs and LLMs are actually much smaller than the complexity for transformers. And the thing about transformers is that you have to compute the correlation between every single input in the sequence. And you're basically doing a parallel computation, which is what the next entry in the table is, which is that for parallelization, the only case in which you can do parallel computations is transformers. in both RNNs and LSTMs, there's no parallelization. You have to go sequentially. You have to go causally. So it becomes step by step. So the thing is, if you're trying to do, a large complexity model evaluation for these inputs, parallel computation kind of makes the whole thing better. It kind of makes it much more effective. And again, the memory usage for transformers is much, much more than the memory usage for RNNs and LSTMs. But again, because you can just do parallel computations, you can just get a good GPU and you can actually just run off it. And again, because context handling is worse with RNNs and LSTMs, they're going sequentially, so they're not really that effective. But with transformers, you have parallel correlation computation, so the context is being computed much better. So yeah, now there's two ways of optimizing transformers, and two ways that there are many ways to optimize transformers, but the two ways that I'm really interested in are knowledge distillation and adaptive or learnable sparsity models. So this talk was supposed to be on the second thing, because I actually have a paper, but at this point it's kind of semi-theoretical and I'm trying to hard code it. So I decided not to really talk about it. But yeah, there are some fascinating links to scaling laws which are yet to be clear. But the basic idea of adaptive sparsity models is that, with vanilla transformer models, you compute the attention weight with the softmax function. And the softmax function is proportional to the exponential for that particular weight. So this value can never be zero. And because it's never zero, all the entries are supposed to be non-zero as well. And so you just call that dense. So that's the dense nature of attention weights in the model. And the issue with this is that you can have non-zero correlation between really irrelevant words in a sequence. Maybe they're just typos, maybe they're just utter garbage strings of letters or numbers, and they'll still be able to affect the other, the more relevant tokens, right? So because you have this non-minimal relevant input correlations, your overall model accuracy kind of decreases. And artificial clipping might help, but it's not really clear how to do this right, because you have to find a very particular threshold so that you make sure that for your attention weight calculation, you're not really cutting out very little relevant tokens. So if something is very little relevant, but it's still relevant in a sense, you don't want to just flip it out and set that to zero. And so Correa et al. In 2019 came up with a paper called Adaptive Sparsity Transformers, and they changed this problem. They kind of mitigated this problem by replacing the softmax function with an alpha nmax function. Again, there's many technicalities with this, but superficially, the idea is that you allow this model to be sparse, because if you have very irrelevant input tokens, you can just set the attention weights for those to be zero. And it's not fixed, it's not a static model, so your alpha can actually vary. It's a dynamic quantity, and you can just treat this alpha as a learnable dynamic parameter. You can just use something like gradient descent, and you can basically use that to make the model more and more accurate. And this model makes the complexity go down from order n squared, as we saw in the previous case with vanilla transformer models. But again, it's not exactly clear whether or not that kind of changes the performance and accuracy trade-off. So overall, how does the complexity accuracy trade-off work, or how do the scaling laws look like, and how does the performance-wise dynamic change with GPUs and TPUs? Well, I don't really think it's very clear. Yeah, that's still an open question. And to be a little more philosophical, if you could allow me to be so. So AI safety is very important, because when you're feeding it huge training data, in some cases, public domain entries for this training data, because in most of the cases, you could just use something like Wikipedia entries, or you could use, archive papers, you could use all sorts of things. You have to be sure in the pre-training that you're not giving it some really, really stupid or really garbage or, corrupt or malformed chunks of data. And so, yeah, you could like effective accelerationism, but, you can't just keep it at an arbitrarily high cost. So it's better to just ensure ethical and moral grounds for AI, and ensure that they're concrete before you actually make a really huge technological leap. So you don't want some weird people to just ask your LLM how to make a malware or make a code for illegal web scraping. And so you'll have to make sure that you you basically filter out and prevent issues like prompt injection attacks or unintentional unethical data in training and so on and so forth. So for instance, in the case of Bard, which is run by Google, or in the case of, well, in general, any PDF to text reading large language model, what you could do is you could give it a corrupt PDF or a doc with a hidden or disguised prompt injection code and basically send a GET request to some attacker server with the information in the URL because it's a GET request, and you can just kind of encode whatever information is present in the PDF or the doc, and the attacker could just read off of that URL and just get sensitive data, and that's bad. And fortunately, this doesn't happen with high-level large language models, which are popular, but it's still very important to make sure that these sort of things are considered firsthand. And in fact, it doesn't even have to be so high level. It could just be corrupt or malformed training data. You could ask it some question, and it would give you some really arbitrary answer, and it would just make your LLM make really bad predictions or produce misinformation, which is obviously not something you want. And in particular, from a code development point of view, because a lot of software engineers and a lot of coders actually nowadays use things like ChatGPT and Flat 3.5 started, myself being one of them. It's really very important to ensure that LLM generated code lies within these ethics and copyright conditions. And so when you use something like Google Colab, and in fact, if you use Google Colab and you use Gemini, and you basically say, oh, this is my piece of code, there's an issue here, I want you to solve it, it basically gives you a warning. And when you add it into your code from auto suggestion, it shows the citation for the words for that code entry, which is very good because that way there's no copyright issues, there's no unethical use of codes from places that you might have just extracted from for training data, and there's no issues with the ethical or the moral grounds. And arguably, I recently had a debate about this. When you're having text to art, for instance, generative models, these ethics become more stronger and more difficult to base on, because in principle, can you just say that generative models are iterating and basically just plagiarizing someone else's art design? And is that even ethical in the first place? So yeah, there's a lot of moral and ethical grounds to keep in consideration. But yeah, this is just the more dystopian side of artificial intelligence and machine learning and large language models. And so yeah, just to conclude, LLMs are awesome, and you can make a GPT-like language model yourself, assuming that you have the money, compute, and time for it. And again, unless you're OpenAI or Anthropic or Google, you probably won't have enough resources to make a very, very sharp GPT-like or 3.5 sonnet-like model. But there's many ways you can just optimize and get a very good model out of whatever limited resources you have. And there's many interesting problems to work with, and there's many factors to take into consideration, and at the same time, ethical principles to stick to. And yeah, again, this talk is not really that formal, but it is really worth it to work with LLMs. And I'm just going to stop with a little pun, which is thank you for your attention. And yeah, okay. So I'm going to stop right here. Thank you.
Yeah, great talk. Okay, can you hear me? Great talk. You need to go back to your side. Yeah.
Sorry?
You have some variables in your complexity NNDs. What are those?
In the table?
Complexity. You had a graph where you put the comparison between transformers, LMPS, and no. Yeah, the complexity you have is NDs. What are these NDs?
So N is basically the sequence. So basically, okay. So there's two things over here. So I really didn't want to involve, the D factor because again, it's basically the hidden dimension. I didn't want to go into the details of this, which is why I actually put a proportionality sign for memory usage because I started out with. But you should just take the n as being the it's you should just take the complexity as being calculated by the order of the input sequence for the context that you could have at most. So this was basically the context size. It was supposed to be n. I think I had, yeah, it was supposed to be n context, but I kind of just changed it with a small n.
What is D?
So D is the hidden dimension. And so the thing is, there's like an additional factor here. So the thing is, okay, again, it would be going a little too much into the technicalities, which I don't really want to do. But the thing is, when you have, you know, a transformer model, typically while your complexity is high, even if you ignore D, it's like order n squared instead of being order n because you're taking every input and you're computing the attention correlation with every other input. So there's basically n times n computations that you have to make. The thing is, if you take the transformer model, which is again very complex and for which the complexity is very high, the thing is because you can do parallel computations, TPUs and GPUs make a lot of use of that, and so that's one of the reasons why this order n squared is not really that much of an issue. It is still fine, but again, it really depends on the use case. So yeah, the
For
D is.
transformers, you need more GPUs.
Sorry.
For transformers, you need more GPUs because they are parallel computations.
Yeah. So because, yeah, I mean, so intrinsically, if you have, TPUs, this is not an issue because they're kind of completely based off of these parallel computations in mind. But the thing is, if you're using a if you're using a transformer for a very simple use case, you're actually, making things much worse for you because you could just use a recurrent neural network and get a really good you can just get a very good effective output. But the thing is, yeah, so transformers are not actually computationally easier, nor are they comparatively better in terms of how many resources or computer time you would need. But yeah, I think well, it's a large language model.
Transformers are bidirectional. Am I right?
Yeah. So the thing is, so you had causal. Yeah, I actually made a remark about this somewhere. Yeah, I'll just stick here. So the thing is, the original transformer model was so basically it was intrinsically bidirectional because you could compute the correlation with everything else. And this is assuming I'm not really mistaken because it's been a while since I read that paper. But the thing is, the other sort of transformer you could have is just a causal transformer, which is I think also called the masked transformer or something. And basically, in that case, the context is always forward propagating, like in recurrent neural networks and their vanilla case. So the thing is, nowadays, most of the transformers are actually bidirectional because your context could be in the future or it could be in the past of the sequence. So yeah, it's really important that you're not doing anything causally.
But then, of course, if you're doing bidirectional, if you can simultaneously go forward and process it and go backwards and process it, of course, that makes sense that it is going to use more resources. But that also makes it kind of non-linear, yes? I mean,
so actually, here's the thing.
I don't know.
The thing is, you're computing
There's
the
always a
attention rate.
branch you can.
Yeah, I mean, there's just one remark actually. Because you're computing the attention rates parallelly, I don't really think it makes much of a difference because you could just, in principle, just take the attention rates and just make you can basically have the context at once. There's no, I think it's just a subtle, like, I don't know, it's more or less a semantic issue more than it is a mathematical problem in terms of whether or not it's causal or bidirectional. So yeah, I think because you're computing the attention rates in parallel anyway, I don't really think it makes a huge difference. But yeah, I do know that there's. Oh, sorry. Yeah. Go ahead.
What were these attention weights, by the way?
Sorry, what?
What are these attention weights?
Sorry, I think there's like a um,
I
yeah.
yeah, I'm asking what are these attention weights?
Oh, the attention weights are basically okay. You could just think of them as giving um, contextual relevance weights to every single input. So if I have a really huge sentence, then I can basically kind of assign for every single input some weight and then make the contextual computation. So yeah, it's actually a very, very interesting thing that attention is actually, it's it's kind of like the genius of the transformer because the thing is you could, in principle, just rely on RNNs and OSTMs and calculate these contextual, uh, you could just calculate this contextual relevance from there. But again, the thing about attention weights is that attention um, blocks is that there's basically um, a sort of a relevance weighing for every single input. And you do that with the softmax function. And to be clear, okay, so the softmax isn't something that's restricted to only transformers. It's also used in both the other cases. But the thing is, when you in transformers, you're basically computing these self-attention in terms of large sequences of matrix multiplications. So yeah, that's where the whole attention heads and the query key value sort of thing pops up, where you're basically taking whatever the input is, and then you kind of work with the context, and then you do the attention weighing, and then you kind of move on, and then you do the parallel computation, and so on and so forth. So yeah, I think yeah, I probably should talk about this, but the thing is, I don't really know how to do it without going in a proper sequential manner, starting from what makes a transformer different from RNNs mathematically. So I think I won't really
Yeah,
go into much detail. Sort of.
that's so, that's a great thing actually.